If you've never struggled with 3D printer ooze before, this is what it looks like. And it's probably the most difficult part of using dissolvable support on most printers. Stick around and watch me struggle. Okay, that's great. It's just sloppy goo in there. Welcome back to Cloud 42. I'm James. When I got my first 3D printer 6 or 7 years ago, I had high hopes of being able to print complex parts using dissolvable support material, just like the big boys on the big Stratasys printers at work. So I designed and built my own double extruder system for the printer and got to work. And what I discovered is it's a lot more complicated than it looks for a couple of reasons. The first is oozing. It turns out if you've got two nozzles on your printer and they're both moving together, while one of them is printing, the other one is dribbling molten plastic on your part. And worse yet, when it comes time to print with that other nozzle, it's now lost its prime, so it doesn't start extruding right away, and that causes all kinds of problems. The second issue is the availability of good dissolvable support materials in the hobbyist market. You've got PVA that you can use if you're printing PLA, which I generally am not. You can use high impact polystyrene or HIPS when you're printing with ABS, but then you have to break it away or you have to dissolve it with solvents. And I really didn't want to mess with that, so I kind of gave up on the dream and put that on the back burner. Until just recently, I noticed a new high temperature dissolvable support material that's readily available, at least it's new to me, and I decided it was worth giving it a try. And this is that story. Oh, and by the way, if you're a 3D printer manufacturer and you have a dual extruder printer that solves the oozing problem and you want to send me one for testing, let's talk. This is the support material that we're going to test today. This is called Ionic, and it is sold by MatterHackers, and they sell this as what they call a hybrid support material, meaning you can use it as a breakaway support or as a dissolvable support, or a combination of the two. And it dissolves in warm water, according to their claims. We will test that. And supposedly it will bond to other plastics well enough to print, but then break away easily. We'll test that as well. Now, what's different between this and something like PVA? According to what they claim, this prints with a nozzle temperature between 240 and 260 degrees Celsius, which is quite a bit hotter than you see with, like PVA support materials, at least the ones that I'm familiar with. And so that makes it, again, according to their claims, compatible with higher tech materials or engineering materials like ABS or ASA or PETG or nylon. And so that's how they have this marketed, and we'll do some testing today. We're going to test with this Carbon X PETG with carbon fiber. This is something I showed in a previous video that I'm really quite happy with, but what we're going to be testing today is the combination with the Ionic support to print geometries that are hard to print independently. Now let's talk a minute about price, because if we don't talk about it here, you'll all be talking about it down in the comments. This stuff is not cheap. They sell this in a 750 gram roll for $120. So it's like $160 a kilo. That's pretty pricey, and you have to put that in context of value-based pricing. So is that worth it? Well, it depends what you're trying to do with it. If you're trying to make small machine parts, which is what I'm trying to do with it, and I would otherwise be manufacturing these parts using some other process that takes a lot of time, but I can instead drop this on a printer and get a small part this size printed for $10 worth of material without me having to sit there and manufacture it. That's worth it to me. If you're just doing this as a hobby and printing things that are going to sit on a shelf, well, you're going to have to decide if this stuff is worth it for you. Now, I didn't actually pay for this roll of filament, but it was not for lack of trying. This stuff has been out of stock for a long time. I've been patiently waiting, and I was ready to plunk down my money when MatterHackers actually contacted me after seeing a previous video that I did featuring one of their other filaments, which they also didn't pay me for. And they said, "Hey, thanks for the free publicity. Can we help you with anything?" And I asked when this stuff would be available again. And they said, soon, and we'll just send you a roll. You can try it out. So that's what they did. They sent me a roll. There will be links to this and the Carbon X material I'm using down in the video description, and those are affiliate links. I have really no intention of trying to sell their products. Wait to the end of the video to decide if this is something that's actually something you want. But if it is, and if you decide to go pick it up, if you use the affiliate link, it's something that helps out the channel. If you don't, no worries, you do you. I've been experimenting with this material for about a week now, and here are the results in order from initial failure to probably some parts that I can actually use. And we will go through these in detail and look at them, but first let's talk about settings in your slicer for support material. This is the first model we're going to use for testing, and I have this loaded up in Simplify 3D, which is the slicer that I use, and let's go take a look at the settings I'm using. So I do have 0.4 millimeter nozzles, and I am printing 0.25 millimeter layer height. 0.2 is traditional, but 0.25 prints faster, and it's usually got plenty of resolution for what I do. So we are going to add a few things to the print rather than just printing the model itself. We are going to use a skirt or brim. That'll print some lines on the bed around the outside of the material of the model just to prime the extruder before we start. And I'm just doing one layer, 2 outlines, 5 millimeters from the part. We are going to use a raft with 3 top solid layers. The raft will give me a nice clean bottom of the support material. I'm going to use the right extruder for that, which is where I'll have the Ionic loaded. And that will allow the part to sit on a nice clean layer of the support material, so we shouldn't have any elephant's foot, and we should get a nice clean bottom and accurate dimensions. And I'm going to use an ooze shield because no matter what I do, this thing is going to dribble somewhat, and we'll set that 2 millimeters from the part, and we'll start with a single outline. I'm going to start with a waterfall on this part so that the top part of the ooze shield will close in and hopefully use less material. For support settings, I'm going to automatically generate support with 1 millimeter resolution, so it should get in everywhere. Again, the support's going to be the right extruder, and the dense support is the right extruder. The difference here is that most of the material is going to be built up at 30%. And then the dense support will be put on top, and I'm going to have 3 layers that are dense support at 100% infill. That'll give me a nice smooth top on the support for the model material to build on top of, and since it's dissolvable, we're going to have vertical separation layers set to 0 on the top and the bottom, so the support material should be firmly bonded to the part, and that should not be a problem at all because it's going to dissolve off. The one other setting in here that matters is the tool change retraction distance. So when it switches from one nozzle to the other, this is how far back it's going to pull the support material. I'll start with 12 millimeters and we'll increase that if we need it. So let's take a look at what this looks like. And on this part, it's completely enclosed in the ooze shield. So we start with our skirt or brim around the outside to prime the nozzle, then start building the raft, and then on top of the raft we'll start building the part, and you can see the outline there is the ooze shield. Every time it switches, it prints a perimeter with the nozzle it's switching to help it prime, and that will build up. And then you can see the support material starting right here in this pocket, and that builds up as the part grows around it. More support material back here. You can see this is the 30% density, and it'll keep going until we get right up to the top, and it closes it in at 100% for the last couple layers to build nice and smooth over the top of that, right up to the last pocket and the top of the part. We've also got this part that we're going to use. This is the encoder mount from the electronic lead screw on my lathe, and this has got a nice big flat area that's unsupported on the bottom. And so this, similar settings. The ooze shield is around the outside as the part builds up, and then here on the top we go to 100% infill and then build over the top. That looks nice and clean. And then the last part that I want to test with is this. This is a cradle that holds an electronic auto darkening welding lens, and then has the geometry for the bayonet mount to fit on the end of my camera lens. So the idea is I should be able to snap this onto the camera, drop in a welding lens, and get some arc shots of welding in the future, and we will see how that goes. But this part is difficult to print without support. You can see that this rim sticks down further, so that's the only thing that would touch the bed. Then we've got a region around that that's lifted up off the bed, and then a region around that that's lifted up even higher. Now, I could make the bottom of this flat and make this mostly printable, but these hooks on the sides would still be very difficult to print without support material. So this is one of the first parts that I've designed without any flat surface to go on the bed, and this is a good test of the support material, and we should do basically the same thing. Build up the raft, and then start building the part on top with support, solid layers of support underneath the part material. And we've got support material coming up here on top under the clips, and we'll just build that up and build the clip on top. This is interesting. Here's a place where the model material is starting in the middle of the support. We'll see how well that adheres and if we get a nice clean print. Well, and that is everything. We'll send these to the printer and see how they turn out. The first couple of prints here were me just trying to figure out the retraction settings. You can see we got through the raft, it printed, but you can see there's a fair bit of ooze from the carbon fiber material in the raft while it was printing. And when we got done with that and actually started printing the ooze shield on top, there was a part in the middle here that I don't have. I must have thrown it away, I'm not sure where it went. But the ooze shield did not stick properly, because by the time we got through all of this printing, we got to and started trying to print the ooze shield. The nozzle wasn't primed, so partway around there was no extrusion on the first layer, and it very rapidly just broke off and I aborted the print. In order to try to make this work better, I started messing around with the temperatures. I lowered the temperature on the carbon fiber PETG as low as I thought I could lower it, to 240 Celsius, and started again. And that reduced the ooze enough that I got a little bit further. And if you look at this, the PETG actually printed and laid down really nice on top of the raft. And you can see that bottom layer is actually quite nice. I'm very happy with how smooth that turned out. But I got up to this point, and you can see the first little pocket in the part starting to be formed there. And there should have been support material in that pocket. But when it came over and tried to print it in there, it had lost its prime, and the initial material just did not stick down. It rolled up and stuck to the nozzle, and as it kept going, that kept rolling up and sticking to the nozzle, so I wasn't getting my filament down in there. In fact, here's a blob of it that had stuck to the nozzle that I later pulled off with tweezers. So, complete fail. And this is the third attempt. And what I changed here is I changed the thickness of the ooze shield. And you can see at the top here, it's only the carbon fiber material. There's no support material up this high, so the slicer switched over from printing both to just printing the one. But this is actually 4 thicknesses. So there's 2 runs around the part, around the ooze shield of each material. And that allowed it to then, it wouldn't extrude initially, it would get partway around, and then on the second pass it would stick to itself. And so there was something there for it to stick to, so even though it was losing the prime, it managed to hold together and printed up this high. Now, of course, the downside of this is that you use a lot more material. This is like 45 grams total, even though the part is only about 14. So that raises the cost quite a bit. And you might be able to see here, it didn't actually print all the way to the top because the extruder jammed. It didn't jam, the drive gear started slipping, and the reason for that is, I think, because I had lowered the temperature too much, and at 240 it just was not reliable. I tried some other prints, got the same results. But let's crack this open. You can see where the ooze is wiped off on the ooze shield. It did its job. Let's crack this open and see what's inside. And this being a hybrid support, like they said, it does just snap right off the bottom, like they said it would. And that bottom surface looks really clean. Let's see, can I get it out of here? I've not actually done this, so you're seeing this the same time I am. Okay? You can see the support material in there, and you can see there are quite a bit of holes in it and places where some of the ooze actually ended up inside. And this actually looks pretty okay. We've got the dissolvable support material. I can break that off. And that surface, that looks really clean. That's cleaner than any of the overhangs. I actually printed some just with overhang, and I don't know how well you can see the difference between those. With this filament, the texture is hard to tell, but this is much smoother where it was sitting on top of the support material. Now we've got some material inside here. Yeah, that is not going to come out, and we've got dissolvable support inside the channels here, and this we're going to try to dissolve here in a minute. But overall, the part looks pretty clean. I've got some ooze in here from as this thing was printing. The surface finish looks pretty comparable to just printing the part freestanding. It turns out this part didn't really need the support, and I figured that out later. This is another one that I said, died partway up. It's not finished because the extruder drive started slipping. I raised the temperature later, and that solved that problem. But this looks okay. We'll try dissolving the material off of this soon. For my next attempt, I did a couple of things. I raised the temperature back up on the carbon fiber material back up to 250 so that it wouldn't jam, and that seems to have solved that problem, but of course it resulted in a lot more oozing. Nice big hairy part. I went back down to just the 2 loops or the single loop of each material. I did a couple of other things. I went ahead and added a brim around the outside to make sure the nozzles were fully primed, and I increased the retraction from 12 millimeters to 24 millimeters. Now with some hot ends, this is pretty dangerous because you're pulling the blob of molten material back up in the extruder or back up in the hot end to a point where it can cool and freeze. I'm running E3D V6 hot ends that have a polished interior, and if you get high enough, they have a PTFE tube, and I haven't had any problem with that at all. So the 24 millimeters worked fine. You can see that I actually did lose the prime, and there is material missing here on the outside, but probably because of the shape of the ooze shield, it ended up not being a big deal. In fact, all the material that's missing right here, you can see it's over here on the side. Let's see what the part looks like. It's crumbling. Okay, so it's breaking off of the carbon fiber material, but the support material that's up inside, it's sticking to that. So it's sticking to itself. That bottom surface looks nice and smooth. Let's see if we can get the ooze shield off. And then inside we do have some ooze on the side of the part here. That's pretty solid. The rest of this surface, it is rougher, right? Because there is some ooze from where it crossed the perimeter, and you can see I've got some ooze on the side here. Some of it's embedded partially in the part. But in terms of the top surface quality and just what I can see without removing this, oh, it's very, very rigid. I'm not going to be able to break that out. This is going to have to be dissolved as well, and then we'll see what this looks like. But so far, that surface looks pretty good. So then using exactly those same settings, I printed this, and this is the holder for the welding lens that I want to go on my camera. So there's a bayonet mount on the inside. This will lock onto the camera, and it's got tabs to hold a welding lens. And let's see how we did here. Let me just pull the ooze shield off. Okay, that's the raft, and then here's the solid support attached to the carbon fiber PETG here. Well, and so far their claims of breakaway material, it actually seems to be working really well. Well, that looks really good. I do have some ooze on the inside surface here, but it comes off with just a fingernail. Yeah, that looks pretty good, and that bottom surface looks good, and it seems flat to me. And then we've got the material in here. Can I pull that out? I think I'm going to try to dissolve that too, because I don't want to. Yeah, I don't want to break these off. So the idea is this will bayonet lock onto the front of the lens, and that should dissolve or at least soften to the point where it can pull out. We'll have to give that a try. This is my ultrasonic cleaner, and I've got about a gallon of water, about 4 liters of water in this. This is a 6-liter cleaner. and I've got it preheated and to about 50 degrees Celsius, and we're just gonna drop these in and see what they do. Now, I assume, oh, they are. I wasn't sure if they were gonna actually submerge. Oh, they are, they're gonna sink. Well, some of them are gonna sink. Hot, hot. And let's see what this one does. Oh, good, they're gonna sink. So at least some of them are. Well, all the support material is sunk in there. So we've got them in there in 50 degrees Celsius water. I have no idea how long this stuff supposedly takes to dissolve, but from everything that I've read, the ultrasound is a good way to speed it up. And I know that's what they use on the dissolvable support material for the Stratasys ABS system. So let's give it a try. Okay, I ran the ultrasound for about 5 minutes, and then these have been sitting here for an additional 2 minutes because there was some other noise that made it hard to film. Let's fish these out and see what's going on. Okay, that's great. It's just sloppy goo in there. Okay, well, if there was any question of whether it was going to dissolve and how long it would take, well, it's dissolving. And it's not taking very long. Okay, I'm just scooping this out. Let me get a rag here. Go ahead and jump in the comments, tell me I should be using rubber gloves. It's water soluble, so I'm assuming this is not a big deal, and I didn't see any warnings about it, but you know, go ahead. Okay, so that's definitely dissolving, and I have no doubts that will continue to dissolve. Oh my goodness, look at that. Okay, that's a big sloppy, soupy mess. Okay, I'm just gonna run this for another 5 minutes and we'll see where we end up. Okay, that's another 5 minutes of ultrasound. And look at me, I got a glove. And let's see, I've got a toothbrush here. Let's see how much of this comes out. And the answer is a lot. Definitely still some in there. Let's see about down in the channels here. Yeah, that's still pretty solid because it is melting down through the channels, but it hasn't gone in. Oh yeah, look at that. I can push it out. Not in that one yet. Not fully in that one yet either. Now I probably could just leave this in here and it would all dissolve, but I want to speed it up, so I'm just gonna apply a little bit of agitation here with the brush and kind of scrape off the big clumps. Yeah, so some parts of this are almost completely clean at this point. And that's after only 10 minutes of agitation in just warm water at 50 degrees Celsius. Okay, well, let me put it in and run it for a few more minutes, and I'll bring you back when we're about done. Well, let's see where we ended up. We've got a total of 25 minutes into this now. And that looks to me like we are pretty much dissolved. I think at this point we've sort of hit the diminishing returns on this water. I imagine it's saturated and we need to start with some fresh if we want to dissolve any more here. Yeah, let me take these inside. Let me rinse them off with warm water and let's see where we are. Well, I spent about 10 minutes at the sink scrubbing these under warm water with a toothbrush, and this is the final result. Now, some parts of this I'm extremely happy with. If you look at the underside of this surface that was supported by the dissolvable support filament, it is very, very smooth. It's basically perfect. And the same thing with the parts of the print that were supported on the raft. And in this case, this was the surface that was down. And you can see that that surface that was against the support material This edge was against the raft, this was against support, this step was against support, and it looks really good. I'm really happy with that. Now, if you look around the outside of this part, however, you can see there's a lot of zits and blobs, and that is, for the most part, ooze. There's a couple of things that are happening. This is ooze that got past the ooze wall and actually stuck onto the part. Same with this, and I've got, ooze on the sides. You can see these little zits and blobs. That's ooze that got past the ooze shield. And there's a little bit of that around the sides, there's a little bit of that down the front. The stuff, though, that was actually supported and had the support material against it, like the underside of this arch, is actually very, very clean. Though if you compare it to one that was printed standalone, you can see it is a little bit cleaner. There are a few filament strands that hung down right there. If you look at the back, up here under the top where there was support, that is nice and clean compared to this one that was printed. This is PETG, this is the carbon fiber one. You can see the strands hanging down here, and there's none here. That's nice and solid. That all worked great. The channels through this are nice and clean. The zip ties go through them very, very cleanly. However, it was difficult to get the plastic to dissolve out of those narrow channels. I spent most of that time at the sink with a dental pick under warm water, kind of picking that out. I'm pretty sure that in the ultrasonic cleaner, I think I overwhelmed the water. I think it was saturated with the amount of material I asked it to dissolve. I think if I'd changed it and run it for a little while longer, these eventually would have dissolved out, but I just did it at the sink. So that's okay. I mean, we got the zits and blobs from the oozing I don't like. The other thing is, if you look at the inside of this wall here on this part, you can see there are a bunch of artifacts on the wall in there. And what that is where the support material was in contact with the wall. When I printed this part, I set it so that the filament would be, support had 0 separation from the wall, so it was actually touching it. And all the places where it touched, there are artifacts in the surface. Not happy with that. On this part, however, if you look down inside these channels on the sides here, they are very, very clean on the inside there because I set it to be 1/2 millimeter away from the wall when I did this part. So the underside that was supported, it's hard to see, but it's very clean. This that was supported was very clean. And because of the geometry of this part, there's not really a lot of ooze. There were some little zits around the inside here, and part of that, you can still see a few of them right here on this edge, but they kind of come off with a fingernail. And so I think this part, because of the geometry of this, it printed pretty well. And I'm pretty happy with it, and I would definitely recommend keeping the support filament off the sides. So, is it worth it? Well, it depends. If you need to print mechanical parts that you just can't print without support, is this easier than using self-support and breaking it away on reinforced filaments or some other solution? Maybe. I think it comes on a case-by-case basis. Given the cost of the filament, I think I would need a pretty good reason to do it. But on a part like this, yeah, I would definitely do it again, probably. On a part like this, yeah, there really wasn't any way to print this without support. And with the thinness of the edges here, I really don't think I would have been able to do that with breakaway support in this particular material. Let's take this over on the camera and see how it fits. Looks like you're gonna get to see a little bit of how the sausage is made. Let me take the lens hood off of this. And this lens has a bayonet mount on the front, and the geometry for that is designed into this part. So I should be able to just lock it on. And sure enough, that fits great. Take that off and grab the welding lens. This is just a cheap eBay welding lens, electronic. So it's got a couple of batteries and a solar cell. And that fits perfectly. I had a bunch of people asking me why I spent so much time when I was making that part for the plasma table, dialing in my parameters to get accurate dimensions on this carbon fiber PETG material. And this is the answer to your question. This is why I spent my time doing that, because this part probably cost about $10 between the material to print it, plus all the support material, plus all the excess material for the ooze shield and the raft. And I was able to print this once, and this fits perfectly. And I would not have been able to do that if I had not dialed in the material first. So I am very, very pleased with that. So the bottom line on the Ionic, do I recommend it? Well, it really depends on your application. In this case, I wanted to print something like this. The cost of the filament was totally worth it to me. And it works pretty well, but the ooze issues on a traditional dual nozzle 3D printer, they're gonna be a challenge. And so definitely do not go buy a roll of this and start experimenting with it unless you're really ready to try to spend some time taming the ooze, because it is gonna be challenging. Now there are other kinds of 3D printers with like IDEX independent nozzles. I know that Prusa just announced their XL, which has interchangeable tool heads. I pre-ordered one because I'm really hoping it will be a good solution for this problem, but we'll have to see in 9 months or a year when they actually ship. Until then, I am going to continue to use this material, continue to play with it, but probably use it sparingly because it is pretty expensive and it really is a challenge to get good clean prints. But all in all, it does add a capability to my 3D printing that I didn't have before. Well, that's all I've got for you today. If you enjoyed the video, give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. Let me know what you think. Is a material like this at this kind of price actually worth it for the kind of stuff that you do? Or is that just price you right out of the market? Or are there other alternatives that I should check out instead? Let me know. Thank you for watching.